condition here. I kind of went really quick through yesterday. I want to just reiterate that when we looked at the binomial settings, the four conditions were that there can only be two outcomes. Either you succeed, get what you want, or you fail. The second one was that the trials must be independent. The third one was that there needs to be a fixed number of trials. So you're only going to try so many times, and then that's it. And then the last one was the probability of success stayed the same throughout. So every trial we run, the probability of success stays the same. Now, in some situations, we find ourselves sampling from a finite population. Okay? So we sample from something that we definitely know is finite. There's an end to it. Now, when that happens, we run into a problem with independence. Think about if I'm drawing cards. Okay? So if I were to draw the first 5 cards and lay them out one at a time, would I have independence for each of my trials? So I lay the top card out, lay it off to the side. Then I draw the next card, lay it off to the side, and then the next card. Why do I have issues with independence there? Because the probability is changing. Every time I draw a card and don't replace it, I'm changing the probability of a success or a fail on the next draw, right? So when we sample from a finite population, in some cases we can't avoid it, and what we found is that if we're less than 10%, so if we end up sampling less than 10% of our entire population, we can still assume independence. And the reason that works is if we're sampling less than 10% of the population, when I pull an item out and don't replace it, technically I'm changing my overall probability, right? Everyone understands that concept? But if my population is so large that the sample I'm taking is so small, less than 10%, then the probability change is so small that we can consider it non-existent. Okay? So what we're saying is if we're taking less than 10% of our population for our sample, we can assume that any changes in probability are so small, we won't see them show up in our calculations. Okay? So the difference between removing one item from this big population versus not is non-existent. Okay?
So there's one in the homework district, like 10% of the schools like left-handed or whatever. So is that like an example of
no, because in that case, they're telling the 10% is your probability.
Okay.
They're saying that if you look at the students, 10% of them are left-handed.
Yeah.
What this is saying is, like our Tiger Woods, Serena Williams, David Beckham problem that we ran with simulations, right, where we had cards within a cereal box. So we said that if we wanted to look at that scenario, we'd have to take a box, we'd open it, find out what card's inside. And then we'd grab another box, we'd open it, find out what card's inside, right? Now, technically, you're not replacing those cereal boxes, correct? So theoretically, when you remove one of those boxes, we had a 20%, 30%, and 50% split. Okay? When I remove one of those boxes, technically, I'm changing the probability of getting one of those cards again. So like if I get a David Beckham card, technically the next time I draw a box, I've changed the probability of getting David Beckham or Tiger Woods or Serena Williams because I've removed a box from the population. Does that make sense? But if we think about how many boxes of cereal they create, that removing one box is going to change that probability so minutely that we won't even notice the difference, which is why we were able to always maintain 20%, 30%, and 50%. Does that make sense? So with this 10% condition, what we have to think about is if we're sampling without replacement, if I'm only taking a very, very small percent of the population, I'm still going to be okay because the changes I make are going to be so small, they're never going to affect my overall calculations. Does that kind of make sense? So when you're thinking of this 10% condition, you're thinking, have I sampled more than 10% of my population? So let's say we're doing something with KLHS here. There are roughly 1,600 kids, right? So let's say we had 1,500 kids here. As long as I sample less than 150 students, so 150 would be 10% of 1,500. Everyone agree with that? So if I'm going to sample less than 150 students, then by removing those students from the population, I'm not changing my overall probability enough for it to affect my overall calculations. Does everyone get that? Okay, so I wanted to make sure we got back through this because this is a very important idea, because there are lots of times where we try to run these binomial experiments and we're sampling without replacement. And there's no way around that, so this 10% condition allows us to continue as long as we're not sampling a large percentage of our population. Okay? The other big thing was this idea of the binomial distribution becoming normal. So when we take a binomial distribution, we have a finite number of trials we're going to run. So here we have n equals 10, so they ran 10 trials, here's the distribution they have. And whatever scenario they're looking at here, here they did 20 trials, here they did 50 trials. Now what they're showing is that if you increase the number of trials you run, the more normal your binomial distribution becomes. Okay? So basically what they're telling you here is that if you have a large number of trials, if I was going to flip a coin 20,000 times, if I was going to flip a coin 200 times, okay? If I have a large number of trials, rather than going through that binomial formula, I could calculate my probabilities using a normal distribution. So my mean would be where our expected value was using the formula n times p. Our standard deviation is calculated the same as the formula from yesterday, square root of n times p times q. And then we can use normal distributions to calculate our probabilities. Now, as far as this goes, we're not going to do a lot with calculating using normal distributions because your calculator runs it with that binom PDF and binom CDF. The problem, and the reason they had to come up with this model, is that previous to calculators, we would get problems that had extremely large numbers that would be almost impossible to calculate by hand. So they had to come up with a different way to approximate probabilities based on this distribution. So they noticed that it became normally distributed, which allowed them to make calculations that were much easier to work with. Okay? Now, the big thing here though, because you will be asked this, so while you might not have to calculate a probability based on the normal distribution, you do have to understand that we can only use a normal distribution to approximate if the number of successes and the number of fails are both at least 10. So if I take the number of trials I'm going to run times the probability of success, so n times p, if that's greater than or equal to 10, then I check how many fails I expect to see. So I take the number of trials I'm going to run times the probability of fail, and if that's at least 10, then I can use a normal distribution to approximate. Okay? So, for instance, if I told you I was going to run 80 trials, and there was a probability of success of 21%. Would 80 trials be large enough for me to use a normal approximation? That might be something you're asked. So to check that, I would actually have to go in and check n times p. So if I check n times p, so 80 times 0.21, what do we get? 16.8. So is that greater than or equal to 10? Yeah. So we can expect more than 10 successes, which means now we can check NQ. So if I want to check NQ, that would be the number of trials, 80 times 0.79. Q is the probability of fail, which is the complement of P. So if you take 80 times 0.79, you get 63.2, which is also greater than or equal to 10. So in this particular scenario, I could use my normal model to calculate any probabilities I might have. So what's the probability that I see more than 60 successes? I can use a normal calculation or normal distribution to calculate that. Okay? If you check your NP and NQ, if either one is less than 10, you cannot use your normal distribution. Okay? So the big thing here, to use a normal distribution, you have to have or have to expect at least 10 successes and at least 10 fails. So that is very important that you guys remember that. Okay? So there was the assignment from yesterday. That was the last little bit. Just wanted to make sure we retouched on that. Make sure everyone's on the same page there. So now let's talk about geometric random variables. So geometric random variables count the number of times a process must be performed until a first success occurs. So one of the big things to keep in mind here, a big difference between binomial and geometric. With a binomial, we were looking for a certain number of successes. So we counted how many times we succeeded. In a geometric process, we are only looking for one success. The other big thing is that in a binomial distribution, we had to have a fixed number of trials. So in 10 trials, how many successes could we expect? In a geometric distribution, there are no fixed number of trials because we don't know when the first success is going to happen. So geometric is looking for when that first success is going to happen. Okay? So the key to look for is something to do with the phrase until the first success. If you see that phrase in the question, that's a dead giveaway that you're working with a geometric distribution. If you see a fixed number of trials, that's going to be a dead giveaway that you're working with a binomial. And it's important that you can distinguish between the two because when you read them, they're going to sound almost identical. But they are calculated in two completely different ways. So you need to make sure you know which is which here. So, a geometric setting, just like yesterday we talked about, how do I determine if I have a binomial setting? Same thing here. Geometric settings have 4 conditions that must be met. The first one is the exact same as the binomial. There can only be 2 outcomes. So geometric and binomial use the same idea that either you succeed or you don't. So there can only be 2 outcomes possible in your scenario. The second one is, again, the same as the binomial. Trials must be independent. Now the third one is where we differ from the binomial setting. So the binomial setting at this point said that there were a fixed number of trials. With a geometric setting, we want the number of trials it takes to get one success. So how many times are we going to have to perform our random event before we find our success? If I have a guess at the fourth one, probability has to be the same all the way through. So the probability that we succeed on any one attempt has to be the same every trial. So for the most part, your conditions are almost identical. And again, that's why a lot of times it's very difficult to determine which one you're working with. The big one is that number 3. So with a geometric, we're looking for the number of trials it takes to get one single success. Okay? So, let's determine if we have a geometric setting. So being able to determine whether we can even use the formulas for geometric settings means you need to be able to read through and dissect the scenario. So suppose a cereal company manufacturer puts pictures of famous athletes on cards and boxes of cereal in the hope of increasing sales. The manufacturer announces that 20% of the boxes contain a picture of Tiger Woods, 30% a picture of David Beckham, the rest a picture of Serena Williams. You're a huge Tiger Woods fan, so while you don't care about the other cards, you must get the photo of Tiger. So how many boxes do you expect to open before finding him? So, in our geometric, or in our setting here, do we have only 2 outcomes? What are they? What would a success be? Getting Tiger Woods. What would a fail be? Not getting Tiger Woods, right? So even though there's 3 different outcomes possible, there's only 2 that we're concerned with. We either get Tiger or we don't, okay? Are the trials independent? Think about what I'm doing for a trial. If I'm performing a trial, that means I'm actually buying a box, opening up to see what I get, right? Do I put that box back before I select my next box? No, I don't. But that 10% condition we just talked about, I'm sampling without replacement. I would be taking boxes off the shelves and not replacing them. However, there are so many cereal boxes produced that me selecting a couple at a time is not likely to change the probability enough for us to notice a difference. So, on a problem like this, you would need to say something to the effect that the trials are not independent, but we should be sampling less than 10% of our population, which allows us to continue anyway. Okay, so that would be something I would look for specifically. If it's not independent, you need to mention that 10% rule to continue. Okay? Are we looking for a first success? Yeah, the last question says, how many boxes do you expect to open before finding him? So we're looking for a first success. Will the probability of finding Tiger be the same every time I open a box? Yeah, so since we're less than that 10%, our probabilities are going to be the same throughout. So here, we would have a geometric setting. So want to see how that works? Okay. So, what do you guys think? There's a 20% chance of getting Tiger, 30% chance of Beckham, 50% chance of Serena Williams. How many boxes do you suppose we would expect to have to open? Why 5? Okay, so the probability is 20%. So he's saying 5 of those makes 100%. Okay, so 20% on one box, 20% on the next box, and so on. So you should be able to find one within the 5 boxes. Another way of thinking of that is if we have a 20% chance, if we revert that to a fraction, 20% would be 1 over 5. So one box out of every 5 should contain a Tiger Woods card, right? So what this does is allows us to formulate a formula for the expected value of a geometric setting. If we want to determine how many boxes we should expect to open, we simply need to work with the probability of success. So when we look at this, 20% was 1 in 5, so we should expect to see a Tiger Woods card about every 5th box. Okay? Now what it says is, if you notice, we said 5 boxes is what we should expect. Well, if I take 1 divided by the probability of success, 1 divided by 20%, that gives me exactly 5. Okay? So this is going to be part of our model that we're building here over the course of the next couple slides. So one of the things you might want to write down for a geometric setting, the expected value, the mean of the geometric distribution will be 1 divided by the probability of success. Okay? So any geometric setting, when it asks for the expected value, you're simply going to take 1 divided by the probability of success, whatever that might be. And that answer tells you when you should expect to see the first success. So the interpretation of E of x here is different than in the binomial setting. In the binomial setting, we calculated the number of successes we expected to find in a certain number of trials. The expected value for a geometric setting is how many trials should we expect to run until we find a first success. Okay, so make sure you know how to interpret as well as calculate. Now, how does this pertain to probabilities then? Because with the binomial model, we talked about mean and standard deviation, but we also talked about how to calculate probabilities. What was the probability that we get exactly this many successes? Well, we can do the same thing with our geometric settings. What's the probability that the first Tiger Woods card we get is in the 6th box? Okay? So, if we think about this, we're going to build a probability model here that's going to lead us to our formula for calculating probabilities with the geometric setting. So, think about what we have going on here. We're going to let our random variable x be the number of boxes until our first success. So basically, the number of boxes until we get a Tiger card. Okay? So in our probability distribution down here, what they're asking us to do is figure out what's the probability that the very first box I open has a Tiger card. 20%. If I'm going to succeed on the very first one, that means I have a 20% chance because that's how many boxes have a Tiger Woods card in it. Okay? So the probability that I get Tiger on the very first box I open, 20%. How would I go about finding the probability that I don't find a Tiger card until the second box I open? So think about that scenario. If I don't find Tiger until the second box, what had to have happened in the first box? I had to have found not Tiger, right? So either David Beckham or Serena Williams. So I have a sequence of events occurring. My first event was that I failed. My second event is that I succeed. When I do a sequence of events, how do I combine those probabilities? Adding or multiplying? Multiply. Okay? So what I'm looking at here is I had to open 2 boxes to get Tiger Woods. That means the first box was a fail, 80%, times the second box, which we're saying was a success, which is 20%. So I would simply take 0.8 times 0.2. Now, if we try to expand this now, if I wanted to calculate the probability that I get a Tiger Woods on the third box, what would have had to happen to lead up to that? 2 fails, and then a success. So I fail on the first, fail on the second, succeed on the third, right? So that means I'm going to have 0.8 twice, right? So 0.8 times 0.8, and then times 0.2. I failed twice, succeed once. Probability that I find him on the fourth box, what will have happened? Fail 3 times, and then succeed on the fourth. So now I have 3 fails, 0.8 times 0.8 times 0.8, and then a success. Starting to see the pattern here? So, if I want the probability that the first Tiger Woods card we get is in the 6th box, what does that mean? It means that I failed 5 times. So I take 0.8 to the 5th power times 20% for success. Okay? So then you can plug that in your calculator, get your answer from there. Okay? Now, if we wanted to generalize this, okay? So let's say we wanted a generalized formula for finding the probability that any given box contains a Tiger Woods card. So maybe the probability that the 10th box is the first Tiger Woods, or the probability that the 100th box is the first Tiger Woods. What's happening with our pattern here? What are we doing here? So when I said the probability that the 6th box was my first success, I took the probability of failing raised to the n minus 1. I had 6 trials I was looking at, so 6 minus 1 gives me the 5 fails, which means my 6th try is the possibility. So what that means as far as a formula, to calculate a geometric probability, this is what you do. Take the probability that you fail, raised to the number of fails you expect to have happen, and then times the probability of success. You have to have that one success at the end. Okay? Much, much simpler formula than the binomial. That is the extent of finding probabilities for a geometric. Okay? Now, we're going to talk about how to calculate ranges of probabilities, but that's going to be one that we use our calculators for, so we don't need a formula for those particular types of problems. Okay? So, kind of in conclusion here, here's the important information you need about the geometric model. So we already talked about the expected value. Take 1 divided by the probability of success. Now, it wouldn't hurt to write down the formula for standard deviation. However, since the geometric distribution doesn't have a fixed number of trials, it doesn't necessarily have a certain distribution that we can use to calculate probabilities with. So the standard deviation for this is much less important. We're not going to be dealing with it very often. So the main things you need to make sure you do know, you do have to know how to calculate expected value for a geometric setting, and you do need to know how to calculate the probability for a specific instance with your success. So what's the probability that on this particular attempt we succeed? Okay. Okay with that? All right. So let's go through an example here. And here's where we're going to kind of talk about how to do some things in your calculator, notation, things of that nature. So, Postini is a global company specializing in communications security. They monitor over 1 billion internet messages per day and recently reported that 91% of emails are spam. Okay, so after all their monitoring and sifting through information, they've determined that 91% of all emails sent are spam emails. Okay? Now, assuming that your email is typical and that you aren't using spam filters, if your inbox collects mail overnight, about how many spam emails should you expect to have to go through to find a real message? So, are we dealing with a geometric setting? So are there two outcomes? Yeah, I either have a real message or I have spam. Are they independent? Yeah, each email should roughly be independent of each other. Okay, so we're okay there. Are we looking for a first success? Yes, we are. How many emails should we go through to find a real message? And then are the probabilities the same each email message I go across? Yes, it would be. Okay, so it's a geometric setting, which means we can use our geometric model. Now, think about what this question's asking. How many spam emails should you expect to have to go through to find a real message? What is it asking us to calculate? Expected value. They're asking for the mean of our distribution. Okay? So, we don't want anything to do with the probability here as far as calculating what's the probability of this or that. What we want to know is how many emails should we expect to go through before we find a real email. Okay? So, we got to think about this. What constitutes a success in this setting? Not spam, so a real message, right? Now, in the problem, they told us that we have a 91% that all emails are spam. Well, what they gave us was Q. They gave us the probability that we fail, which means our probability for success would be 9%. Okay? So the probability that we succeed would be 9%. And so if we know that, we can calculate expected value easily enough by doing what? 1 divided by 0.09. So if we take 1 divided by 0.09, 11.1 repeating. Okay? So about how many emails should we expect to go through before we find a real one? Yeah, a little over 11, right? So about the 12th one, we should be expecting to find a real email. Everyone okay with that? Okay. What's the probability that the 5th message in your inbox is the first one that isn't spam? So what they're asking us to calculate here, what's the probability that our first success is equal to the 5th message? So if we think about our probability distribution that we created, if my 5th message is the first time I see a success, what does that mean has happened on the first 4? They've been fails, they've been spam, right? So if I want to calculate this probability, I need to take 0.91 to the 4th times 0.09. Now, could I do 0.09 times 0.91 to the 4th? Yeah, the order's not going to matter because multiplication is commutative, but we do need to make sure that we raise the correct percentage to the exponent, okay? So be very careful with your probability of success versus your probability of fail, because switching those around will make a drastic difference. Okay? So if we take 0.91 to the 4th times 0.09, about 0.063.
It's actually 2, but...
Oh, 62. So 0.062. So there's about a 6% chance that the first message that's real is the 5th message we checked. Okay with that? Now, we can do the same process on your calculator. Okay, so just like the binomial distribution had the formula, there was also a function in the calculator that allowed you to work this out. So, in your calculators, if you wanted to do this using the function given in there, you're going to go to the same spot you did for binomials. You're going to go to second vars, and you're going to scroll up once. Okay? And one of the last couple options on the screen should be Geomet, PDF, and CDF, right? Okay? So, thinking back to yesterday's discussion, what would the PDF be used for? An exact spot where the first success happens. So when they say, what's the probability that the first success happens on this attempt? Okay? So that would be exactly... Okay? So that would be exactly what this question asked. What's the probability that the fifth message in your inbox is the first one that isn't spam? Okay? So, if we were looking at the exact time when we're going to hit a success, that's a PDF. So, if we did this in the problem, go ahead and select that option, Geomet PDF. Okay? Now, for most of you, it's going to take you to a menu where you have to fill in some blanks, right? Does anybody have just the Geomet PDF? Come back up on your screen. Okay, so you're just going to type it in as we say it for the menu. So the first thing the menu asks for is P. So the first thing you're going to type in is the probability of success, so 0.09. So then Julia, a comma. And then it wants X value. When do we want that first success? So in this case, 5. So 0.09, comma 5. Hit paste, hit enter, and you should end up with the same answer, right? Okay? So Geomet PDF tells you exactly when you're going to hit a first success. Is everyone okay with that? Okay. Sticking with this example, what is the probability that the first real message is found before the fourth message checked? So think about the difference here. The last one was, what's the probability that the fifth message is the first success? Now, the wording has changed. What's the probability that the first real message is found before the fourth message checked? So what's that actually asking us to figure out? Within the first 3. So it could be the very first one we check, it could be the second one we check, it could be the third one we check. So if we wanted to, we could calculate the probability of the first message plus the probability of the second message plus the probability of the third message. We could do 3 PDFs. Or we can use the Geomet CDF function in the calculator, which will account for all of those the entire way through. So what this question is asking is, what's the probability that X, our first success, happens before the fourth, so less than 4. So in this case, we're going to choose that Geomet CDF. So go back into your second vars. Scroll up, go to Geomet CDF. And so now, we type in our probability of success, 0.09. And now if we want the probability that X is less than 4, where do we stop ourselves? At 3. Okay, so be very careful, especially when you go to do these CDF problems. You need to make sure you're cutting yourself off at the correct spot. So we're going to cut ourselves off at 3. And when we hit enter there, 0.25. So there's about a 25% chance that we'll find a real message within the first 3.
So we could do PDF and then get that and then just multiply that by 30, basically.
No, if you wanted to do the PDF version,
Yeah.
you'd have to do the probability that x equals 1, which would be 0.09, because you're hitting on the first one, right? You have to calculate the probability that x is equal to 2, which would be 0.91 times 0.09. And then you have to do the probability that x is equal to 3, which would be 0.91 squared times 0.09. And then you have to add these three together. So yeah, the CDF doesn't just multiply by a certain constant, it actually calculates each of these individually and then adds them all up for you. Okay? All right. So now, take a look at this one. What's the probability that the first real message doesn't happen until after the 8th message is checked? So think about what's happening here. Probability that the first real message doesn't happen until after the 8th message is checked. So what would we need to do here? Okay, one option would be the complement. The complement of this would be that we find a first message within the first 8. So we could do 1 minus geomet CDF 0.09 comma 8. Okay, so we could definitely do a complement of it. The other thing we could do is, if we think about this from a different perspective, if I'm not finding the first real message until after the 8th message is checked, what does that mean has happened for the first 8 messages? I have failed. Now, do I know when I'm going to hit a first success after that? No. I don't care. All I need to make sure is that I've made it 8 messages of fails before I find a real one, right? So in this case, I can actually just go ahead and take 0.91 to the 8th. I have to hit 8 fails. After those 8 fails, I don't care what happens. I can find the real message any other time after that. I just need to make sure I hit 8 fails. Does that make sense? Okay. So complement rule would definitely work. Or you can always do this one. With the geometric, since there is no end, we can just do the value this way and call it good. Okay, so this might be an easier version of that type of problem. Okay with that? All right, then there's your assignment.